Hello everyone. Welcome to your next practical of the laboratory practice module of semester 7 Induction Generator. The objectives of this practical are to study the characteristics of operation of a self-excited induction generator and a grid-connected induction generator. Before moving on to the practical, let's get an idea about induction generators. A generator is simply a machine that produces electric power from rotational mechanical power. So, what's an induction generator? An induction generator or a synchronous generator is a type of an AC electrical generator that uses the principles of induction motors to produce electric power. Induction generators operate by mechanically turning their rotors faster than synchronous speed, producing electric power. Induction generator is constructed as same as the induction motor. So, a regular AC induction motor usually can be used as a generator without any internal modifications. Here is a picture of a generator. Construction of induction generator is almost similar to the induction motor. The same machine can be used for both motoring and generating purpose according to the rotor speed. You will learn about this later. A three-phase induction generator mainly consists of two parts called the stator and the rotor. The stator is the stationary part of the induction generator and the rotor is the rotating part. In the center of the generator, we have our rotor and the rotor is free to rotate within the stator. So, everything on the outside of the rotor is known as the stator, which is fixed. The stator core is built of high-grade silicon steel stampings. Its main function is to carry the alternating magnetic field. The rotor is also built of thin laminations of the same material as the stator. The laminated cylindrical core is mounted directly on the shaft. There are two types of rotors named as squirrel cage rotor and wound rotor. Within the rotor, we have current-carrying conductors, and when the machine is in generation mode, it will create current from the movement of the rotor. On the stator, we have poles, and here we have north and south poles, which create magnetic fields, and we can see the magnetic field lines drawn in blue. This graph shows the torque and speed characteristics of an induction machine. As you heard before, the same machine can do both motoring and generating. According to this characteristic curve, it is essential for the rotor to rotate at a higher speed than the synchronous speed to produce electric power. For an example, let's take a 4-pole generator attached to the utility grid in Sri Lanka, which has a frequency of 50 Hz. It has a synchronous speed of 1500 rpm. If the generator is driven above this synchronous speed by external means, the resultant effect will be such that the rotor will rotate faster than the rotating magnetic field of the stator. And the polarity of the induced rotor voltage and current is reversed back to the grid, which means generating electricity. There are various advantages of an induction generator. Let's talk about some of them. An induction generator requires less maintenance because of its robust construction. An ordinary cage motor is used as an induction generator as it is cheap. Speed variation of the prime mover is less prominent. The induction generator is smaller in size per kilowatt output power. It needs less auxiliary equipment. It does not have to be synchronized to the supply line as that of the synchronous generator. The induction generator has a self-protection feature. In the case of the short circuit, if a fault occurs on its terminals, the excitation fails and the machine stops generation itself. Now let's look at where these induction generators are used. Induction generators are useful in applications such as mini hydropower plants and wind turbines. They are also used in combined cycle power plants to reduce high pressure gas streams to lower pressure because they can recover energy with relatively simple controls. As we discussed before, the induction generator is used in many applications. Also, now you are familiar with the construction and working principle of it. So, we'll move on to the next part of the theory. In the operation of the induction generator, real power flows out of the machine, but the machine needs reactive power. To build up voltage across the generator terminals, excitations must be provided by some means. Therefore, the induction generator can work in two modes. They are isolated mode and grid-connected mode. When a standalone induction machine is driven by a mechanical prime mover, the residual magnetism in the rotor of the machine induces an EMF in the stator windings at a frequency proportional to the rotor speed. This EMF is applied to the capacitors connected to the stator terminals and causes reactive current to flow to the stator windings. Hence, a magnetizing flux in the machine is established. The final value of the stator voltage is limited by the magnetic saturation within the machine. The induction machine is then capable of operating as a generator in isolated locations without a grid supply. Now we'll look at the operation of a self-excited induction generator. The diagram shows the per phase equivalent circuit of the machine with the capacitor connected through its terminals. Assuming that the machine runs at synchronous speed, which the slip is near zero, the branch in the right to the XM can be considered as open circuited. So, the circuit resolves to this. Then we'll consider the operation. When the rotor of induction generator is run, the residual magnetism present in rotor iron creates a small EMF across stator terminals. This voltage causes a capacitor current to flow. The flux due to the current is added with residual flux and generates a stator terminal voltage. This voltage produces current in capacitor bank, which then generates a voltage. This cumulative process continues till the intersection point between saturated magnetizing curve and the capacitor load line. The graph in the figure shows the internal volt-ampere characteristics of the two circuit elements C and Xm. Note that Xm is nonlinear, so it exhibits a saturation of the magnetic circuit of the machine. As shown in the graph, the intersection point gives no-load generated EMF at the magnetizing current. Note that the previous assumptions are only valid under no-load conditions. Currents IC and IM can be calculated using the equations 1 and 2. Here, Lm varies depending on the saturation and omega is the angular frequency of the machine at its terminals. The voltage build process depends upon the capacitor value. Higher the value of capacitance, greater is the voltage built up. In the absence of a proper value of residual magnetism, the voltage will not build up. So, it is desirable to maintain a high level of residual magnetism as it eases the process of machine excitation. Then we'll move on to the grid-connected mode of the induction generator. Grid-connected induction generators develop their excitation from the utility grid, and the lagging reactive power requirement is drawn from the utility grid. The induction machine is driven at a speed greater than the synchronous speed. As we have seen in the per phase equivalent circuit earlier, the element R2' 1 minus S over S becomes negative. So, it can be concluded that the machine receives mechanical energy and converts it to electrical energy. The generated power is fed to the supply system. Hope you had a good understanding on the working principle of induction generator. Now we'll move on to the procedure. First, we'll look at the apparatus we are using for this practical. For the induction generator, we use the modes list general machine set. It consists of an induction machine with the specifications shown in here and a DC dynamometer, which is a DC motor. You can see this setup in the figure to your right. Further, we'll need a 3-phase wattmeter, an AC voltmeter of 300 volts, 2 AC ammeters of 5 amperes, a tachometer. Finally, we'll need a bank of variable resistive loads as shown here to your left and a capacitor bank of the range 0 to 120 microfarads. This is shown in the figure in the right. As the first part of this practical, we'll look at the self-excited induction generator. We'll look at part A in your lab sheet, no-load characteristics for varying capacitance and constant prime mover speed. Here we are going to observe the variation of voltage and current of the machine in no-load condition by varying the capacitance but keeping the speed of the machine constant. We have to connect the circuit as shown in the diagram. Have a look. This is the Maudsley's general machine set we are using for this practical. This is the nameplate of the induction machine. This is the DC dynamometer or DC motor used as the prime mover and its nameplate. This is the capacitor bank that we are going to use. These are the capacitors and these are their relevant switches. Here you can see the capacitance and the voltage values marked here. First of all, let's understand the connections. Here, the red color wire, which is the R phase, is connected to the ammeter. The range of the ammeter is 5 amperes. Other terminal is connected to one phase of the 240 volts 3-phase supply. This green wire denotes the Y phase, and this wire from the capacitor bank is connected to the voltmeter and another phase of 240 volts 3-phase supply. Note that the range used is 300 volts. And this other blue color wire denotes the B phase. This wire from the capacitor bank is connected to the voltmeter and the remaining phase of the 240 volts 3-phase supply, as you can see. So, these are the connections of the 3-phase supply. These are the dynamometer connections. Here, the dynamometer or the prime mover is the DC motor. These are the connections for a pole changing induction generator. No need to worry much about these connections. Simply connect the stator winding in a delta connection as shown here. This is the field current control of DC motor. Make sure to keep this at a minimum position at the start of the practical. These are the AC supply connections. This is the switch for the 3-phase induction generator. This is the switch for DC motor. This is the starter of the DC motor. So, after connecting the circuit properly, let's turn on the prime mover of the induction generator. Switch on the DC motor. Slowly turn this knob on the on position. So, you can see it rotates at a speed of 1413 rpm. Now, let's adjust the speed to 2500 rpm using the field current control. So now it's almost 2500 rpm. Now let's measure the residual voltage like this. This is the terminal voltage measured when the terminals of the induction generator are open circuited. This is due to the residual magnetism. It is 2.858 volts. Now connect the capacitor bank at the machine terminals and measure the voltage, frequency of the induction generator, and the magnetizing line current on no load at 2500 rpm. Make sure not to exceed 280 volts. Here we have connected the capacitance of 75 microfarad to the machine. Switch on the capacitance using these switches. You can measure the ammeter reading like this. Note down the voltmeter reading also. Let's measure the frequency of the generator. So turn this knob to Hertz and keep the two probes at two phases of the three-phase supply. And now you can measure the frequency. Likewise, we continue the procedure by varying the capacitance and measuring the voltage, current, and the frequency of the machine. The values we obtained in the practical may be slightly different from the values here in the table due to some errors in the machine. So, use these values when preparing your courseworks. Then we'll move to part B, no-load characteristics for varying prime mover speed and constant capacitance. Here we are going to observe the variation of voltage and current of the machine in no-load condition by varying the machine speed but keeping the capacitance constant. The circuit is same as in part A. As you can see from the given set of readings for part A, the capacitance required to obtain the rated voltage under no load at 2500 rpm is 65 microfarad. So, this is how we should connect the capacitors in order to get the needed capacitance of 65 microfarads. Now, let's increase the speed to 2500 rpm using field current control. Now, connect the capacitance needed to obtain the rated voltage under no-load condition at 2500 rpm. Here, we have to drive the prime mover at different speeds such that the no-load line-to-line voltage is within the range of 200 to 280 volts. We have to take magnetizing current, voltage, speed, and frequency readings for different values of voltages. Let's start by adjusting the voltage to 200 volts by using the field current control. And then take the ammeter reading. Now, let's measure the frequency like this and note down its reading. We continue the procedure by keeping the capacitance constant and measuring the voltage, speed, current, and the frequency of the machine. Here also, use these values when doing the calculations. Next, we'll move to part C, performance of the loaded generator with constant speed. In here, we are going to observe the variation of voltages and currents in different loads of the machine while keeping the speed constant. For this part, we have to connect the circuit as shown here. To vary the loads in the machine, we use a resistor bank. Here we have connected the circuit as before. We connected the voltmeter, ammeter, and the capacitor bank. Apart from that, we connected the resistor bank as shown here using these pins. Have a look at the resistor bank. The resistor bank is connected to the setup through an ammeter to measure the load current. To start the practical, we switch on the setup. Here we have connected the capacitance such that the no-load generator voltage is 280 volts. The no-load capacitance is 75 microfarads. And then we adjust the field current control in order to drive the prime mover at 2500 rpm. As we did before, we can increase the prime mover speed by varying the field current control. As you can see, now the speed is 2500 rpm. Now we switch on the capacitors. We measure the voltage, currents, frequency and torque of the machine by varying the load resistance. Now the load resistance is at 0. This is the voltage of the induction machine, the current, and this is the load current. We increase the load resistance in one step. When increasing it, we have to make sure that the load current doesn't exceed 5 amperes. Now you can see that the speed has been reduced. So we are going to readjust the speed to 2500 rpm by varying the field current control. Now you can see that the speed is 2500 rpm. We measure the generator voltage, current, load current, torque, and the frequency. We further increase the resistance. Here also, the speed is reduced. So, we readjust the speed by varying the field current control. Then, we measure the generator voltage, current, load current, torque, and the frequency. We continue the procedure by keeping the capacitance and the speed constant and measuring the voltage, currents, frequency and the torque of the machine at different loads. Use these values when doing the calculations. Then we'll move to part D, performance of the loaded generator without speed regulation. Here also, we are going to observe the variation of voltage and current of the machine without keeping the speed constant. For this part, the circuit is same as before. Now, we increase the load resistance in one step. As we did in part C, we have to make sure that the load current doesn't exceed 5 amperes when increasing the load resistance. We measure the generator voltage and current. This is the load current. Further, measure the torque, speed, and the frequency. We further increase the resistance and measure the load current, generator current, generator voltage, speed, and frequency. And also the torque. Likewise, we continue the procedure by keeping the capacitance constant and measuring the speed, voltage, currents, frequency, and torque of the machine at different loads. Use these values when doing the calculation. Next, we'll look at the grid-connected induction generator. As we have discussed in the theory, here the induction machine is connected to the supply mains. So here, the induction machine is connected to a 3-phase wattmeter. The connections are made according to this diagram. So you can see the connections here. These are the 240 volts 3-phase supply terminals. They are connected to the wattmeter, ammeter and voltmeter as shown in the previous circuit diagram. You can get a better understanding of how the connections are done when doing this practical physically in the laboratory. First, let's check the direction of rotation of the DC motor. Please observe carefully. Then, let's check the direction of rotation of AC motor. Carefully observe this as well. We have to make sure that both are rotating in the same direction before going forward with the rest of the practical. If they rotate in opposite directions, change the circuit to get the same direction of rotation. Now, let's switch on the DC supply and start the DC motor. Use the field current control to drive the prime mover at 3000 rpm. Here we are using the rheostat connected in series with the field current control to achieve a speed of 3000 rpm. So, increase its resistance until the tachometer shows a reading of 3000 rpm. Now, let's give the grid supply to the induction machine. Here, you can see that the grid is supplying power to the motor. Now, let's increase the speed slightly so that the wattmeter reading is 0. So now, no real power is delivered to the grid. You can see that the machine is rotating at a speed of 3026 rpm now. Similarly, we have to take the line current, voltage, frequency, power and torque readings under this condition. Please note that this part is not shown in the video. Here, the ammeter reading corresponds to the excitation current drawn by the induction generator. Now we have to increase the speed in steps of about 25 rpm. We can do this using the field current control. And then we have to take all the above readings once again. So let's take the ammeter reading. The range is 5 amperes. Let's take the voltmeter reading also. Note that the range is 300 volts. Let's take the wattmeter reading. The range is 240 volts and 5 amperes. So, the multiplication factor is 20. Please note that the given wattmeter readings are the values after multiplying with the multiplication factor. Now, let's take the reading of the torque. Let's take the frequency reading too. Since this is operating as a grid-connected induction generator now, the frequency should be 50 Hz. We continue the procedure and measure the current, voltage, power, speed, frequency and torque of the machine. Here also use these values when preparing your courseworks. For the observation sheet, you have to prepare 5 tables as we discussed earlier. There are 4 tables for the 4 parts under the self-excited induction generator and 1 table for the grid-connected induction generator. Then we'll move to the calculations. For the self-excited induction generator, under part A, you have to plot line voltage versus magnetizing current, line voltage versus capacitance, and using the above curves, determine the capacitance required to obtain the rated voltage of 240 volts at given speed and the rated voltage of 240 volts at the rated frequency of 50 Hz. Under part B, you have to plot the curves of voltage versus speed, frequency versus speed, and magnetizing current versus speed. For part C, plot voltage versus load current, frequency versus load current, and generator current versus load current. Under part D, you have to plot the curves of voltage versus load current, frequency versus current. On the same graph sheets on part C, plot the torque versus prime mover speed. For the grid-connected induction generator, you have to plot 4 curves. They are power output versus speed, line current versus speed, efficiency versus speed, and power factor versus speed. Further, you have to discuss the given 4 questions under the discussion. Hope you learnt a lot about induction generators from this practical. Thank you. Have a great day.